All right, so for catalysis, we're just going to be taking a look at this graph here, um, and let me draw a couple of reactions here. So this reaction, and then I'll. So in understanding these, right, that if looking at both of these graphs here, we would say that this one would be uncatalyzed, and that this would be a catalyzed reaction because we're actually lowering that activation energy here, right? So this is, oh, right. So here's our activation energy here, and then the difference here, right? This is our change in enthalpy, right? So our change in enthalpy here um, actually ends up being negative. So we have a negative change in enthalpy there. So enthalpy being equal or being less than 0. So catalysts affect the rate of the reaction. So a catalyst will affect rate of action. But what it doesn't affect is concentration. So it doesn't affect the concentration of the products, right? It doesn't affect that. What it also doesn't affect is equilibrium, right? So again, catalysis will only affect the rate of the reaction, right? Is that we're going to get a larger K value, right? So here, this would have a larger K value, right? The larger the K, the faster the reaction goes, right? So it just affects the rate of the reaction, but it doesn't necessarily affect the concentration, and it doesn't affect the equilibrium. Now, as far as catalysts go, you know what, and we can even take, oh no, we'll do this in the, you know what, no, I better do it before we get there. Because when we're looking at activation energy, is that sometimes, you know, we'll have it go like this, and sometimes, you know, we can have it go like this, right? Where here, this is done in a single step, right? So this reaction took place in a single step, while this was a multi-step reaction, right? That here, because we see the two peaks, that this was a two-step reaction, right? And here, this is our intermediate that's formed here, right? We have our transition state. We have our transition state. We have another transition state. This is where our intermediate is formed. And, you know, then we get our products over here. Right? But we can tell by the type of the graph if by the peaks there of just how many steps that this is going to take, how many intermediates are we going to have. And some of that depends on the catalyst itself, right? Some of it depends on the catalyst. We have two types of catalysts. We have what we call homogeneous catalysts, and we have heterogeneous catalysts. This is the one that I used to work with, the heterogeneous in grad school, so I'm just a little more familiar with that. But homogeneous catalyst, the catalyst is in the same phase, the same phase as the reactant. If my um, reactance is gas, my catalyst is gas. My reactant is aqueous, my catalyst is also aqueous, right? It has to be in the same phase. And the heterogeneous isn't, right? So heterogeneous, the catalyst is in a different phase than the reactant. Now, homogeneous catalyst can be single step, right? Most of them, it's usually single step. They can have multi-step reactions, but homogeneous catalysts are mostly used because they can be single step reactions, right? And a heterogeneous catalyst is a multi-step process. There's a multi-step process that occurs here. That for multi-step, there's phases that we go through, right? There's what we call an adsorption. So there's absorption onto a surface, because again, we're in different phases here. So there's absorption onto a surface. The second step is the activation of the adsorbed reactant. And not absorbed, but adsorbed. The absorbed, and I'll put reactant here, of the absorbed reactant. Step 3 is the reaction of the adsorbed reactant. And step 4 is the diffusion of the product. Diffusion from the surface. So these 4 steps take place when we're doing heterogeneous catalysis, right? A single step reaction can look something like this. We have let me draw glucose out here.
You said those steps are for what again? I'm sorry.
This is for multi-step. This is going to happen for heterogeneous catalysis.
Thank you.
So here, so this is Now, when glucose reacts with something we call hexokinase, right? It's another sugar, but it's going to react with hexokinase. Hexokinase is known as a transferase. And the whole job of a transferase, this is the type of catalyst it is, right? Hexokinase is the actual catalyst, right? But the type of catalyst it is what we call a transferase. So a transferase, just like in the name, is that we're going to be transferring something, right? So the job of hexokinase is to actually transfer a phosphate from another from something else that we're something we call ATP here. And if you've taken biology, you might be familiar with these terms. Um, adenosine triphosphate here. So adenosine triphosphate comes in here and then it leaves as a DP. So it leaves as adenosine diphosphate. So one of these phosphates has been removed and we actually get our finished product. We get here, this would be glucose 6 phosphate. All right. So this is what we would consider single step here, right? The hexokinase is in the same phase as glucose, same phase. This is one step. So one step, single, same phase, uh, homogeneous catalysis, right? As we're using a homogeneous catalyst. So this happens here in just one step. So it's not like a multi-step reaction. A multi-step reaction, let me write some arrows here. So this is, so let's take a look at a heterogeneous catalysis now. So heterogeneous, and I'll write that just so we're clear here, is multi-step. So my drawing's not that great, but I think we can still understand just from my drawing what's going to happen here. So this is a metal surface, right? We're just going to kind of consider this a metal surface. Come on. Metal surface, and we're kind of looking at the top view here, right? So we're kind of looking down at this, and we'll just say that this is, maybe this is nickel, right? All right, so we're going to say that nickel here. So what happens here is that let's take some hydrogen gas, and it's going to absorb onto um, our material here. And then let's take some ethene over here, and that's also going to absorb on the surface. So that is step one, right? Absorption onto a surface. So we see the ethene there and the hydrogen absorbed to the surface. And being absorbed to the surface is just kind of like they're just kind of stuck there. There are electrons on the surface of this material. It's a metal. So this is a metal, and there's electrons all over the metal that are attracting these reactants and pulling them to the surface where they're just kind of lock onto the surface for a little bit. And once they're on the surface, then these electrons react, right? So here we have to activate those. And the electrons on the surface activate those. And we actually end up getting something like this, where it's now these hydrogens are just on the surface here. They're not bonded to each other anymore because the electrons here are breaking those bonds and separating them, right? And then we can have maybe some CH, we had CH2, but how about a single bond of just CH2 now, instead of a double bond of CH2? Let me put a, instead of green here. Now we have to have them react. So we activated them. They're not reacted yet, but we did activated them by breaking those bonds. So now we're going to have the reaction of the absorbed reactants, right? We're going to have a reaction here. So what takes place is, well, now we're going to get CH3. We're going to get some ethane, but this is still on the surface. It's still absorbed onto the surface. And then we finally have, oh, then we finally have what we call diffusion, where that product, that product is diffused from the surface, where it actually releases, and this methane gas can now go out, and it's diffused from the surface of that. But this is what we consider heterogeneous catalysis, right? Because it uses a heterogeneous catalyst. We have something in the gas phase here, and then something here in the solid phase, right? But we definitely had, this is definitely multi-step, um, and definitely have two different phases here regarding the catalyst nickel and the reactant of ethene here. So let's look at just one. I think this is going to be that we'll have. Let's just take a look at this reaction here. We have ozone. Ozone decomposing into just some oxygen, right? And there's different catalysts that can do this, right? Different catalysts that can do this. So chlorine, and chlorine radicals are in the atmosphere. Is there are chlorine radicals like this, they're that break off from just chlorine gas, and we just get some chlorine radicals. So chlorine can actually be used as a catalyst to help break down ozone into oxygen. So that we would put some O3 here. So chlorine reacting with just ozone, and we're going to get here, plus we're going to get some O2. Then we can have this chlorine that's bonded to this oxygen here, react with just some oxygen radicals in the air, right? And then we're going to get back our chlorine, plus we get some more oxygen, right? And in an overall reaction, so this is my overall reaction, right? The overall reaction, we don't put intermediates, right? We don't put intermediates into the overall reaction, and we don't put the catalyst in the overall reaction either. And how are we going to tell? How do we tell the difference between catalyst and an intermediate? Right? There are differences between that. We've gone over intermediates, but let's go over it just one more time. Right? Here's an intermediate. How do I know that this is an intermediate? Right? An intermediate is produced in one step and consumed in another step, right? Remember, does that sound familiar at all, right? An intermediate, we produce it in one step, consume it in another step. But catalysts, is represented here where a catalyst is not consumed in the final step, right? We reactivate that catalyst. The catalyst came in here, reacted to the ozone to break it down. We made an intermediate. And at the final step, we got our chlorine back. So this chlorine is now free to repeat this process, gets another ozone, get another intermediate, break it down into some more oxygen. And in the final step, we get that catalyst back. And catalyst can be used over and over this way, that the catalyst is not used up, right? The catalysts keep going and keep going until we run out of reactant. It keeps going till we're going to run out of ozone. After we run out of ozone, well, then the catalyst isn't needed anymore. End of reaction. But that catalyst is regenerated or regenerated in every single final step until that reactant is used up, right? So that's our difference between this catalyst and the intermediate. The intermediate produced in one step, consumed in another. The catalyst is not consumed in the final step, right? We begin with it and we end up with it. But as far as calculations go, we're not going to do any calculations regarding catalysis. You might see that in maybe physical chemistry or inorganic chemistry, but just kind of our introduction into catalysis here. So I am now